Hi! How can we look at behavior in psychiatry through the lenses of modeling? Behavior is the sequence of events stemming from learning and decision-making. These change and evolve together, where these abilities may involve worse decisions and worse learning conditioning each other, and ultimately suboptimal behavior. Mathematical models can be designed to mimic human behavior, encompassing both the learning and the decision-making components. These models have general parameters that will influence how the sequence of events unfolds. One starts by simulating the learning of a task with different models and parameters, then proceeds to real data, evaluating how well each model fits it, as well as obtaining parameter values. These can consistently be different for a specific subpopulation, let's say with a certain psychiatric disorder. Sometimes these models can even correspond to actual neurobiology, as in the case of temporal difference learning, based on measuring the discrepancy between actual and expected reward, closely describing the firing of dopaminergic neurons. One major family of algorithms is reinforcement learning, which considers an agent performing a task. The task has states, possible actions for each state, and consequent rewards or punishments, while the agent has a policy of choosing a certain action for each state. Often the transition between states, the rewards, and even the policy function are probabilistic, rather than deterministic. Reinforcement learning works by iteratively improving the policy while updating the value function, trying to maximize it. This function attributes a value to each state under the current policy by estimating the next reward plus discounted future ones. Alternatively, one can use a state action value function, which attributes this value to a state action pair instead. This allows for a policy to be read directly from it, like the action with greatest value for the present state. State or state action value functions can be obtained by model-free or model-based methods. The former works by simple experimentation and entry update. The latter involves constructing a model of the environment with state transition functions and reward probabilities, only then deriving the value function entries. Model-based learning tends to be more flexible to environment changes, and obsessive-compulsive disorder is classically associated with a lack of it, with a model-free over model-based imbalance. The reversal learning task provides a good ground for discovering other distinct, possibly more inflexible, behavioral aspects of this disorder. The subject has two choices: one rewarded most of the instances, the other punished most of them. After getting it right several times in a row, the association flips. A good first hypothesis is testing if the speed of learning and unlearning differs between groups. Lastly, reinforcement learning can be extended by considering not only observable states, but also hidden ones, not directly observable, but useful to describe the world better. These are inferred imperfectly using Bayesian statistics in a cyclical process where prior beliefs are updated by evidence to form posterior beliefs. In the reversal learning task, one might test if this kind of cognition is more patent in healthy individuals. Discovering such mathematics behind the disorder can prove useful, not only in diagnosis and quantitative re-evaluation after treatment, but also having possible correlates with neurologic substrates and shedding light on uncharted territory. Thank you so much.